Okay, well, I think we're going to get started. Hopefully everyone online can hear me as well. This talk is going to be about the monocular depth estimation challenge. And specifically, we're going to be focusing a bit more on what the challenge setup is, but also what the kind of motivation behind organizing this challenge was in the first place. If it lets me. Okay, yeah, so I'll be talking first of all about what benchmarking is and why we should care about it. It's an important part of every field. As part of that, I'll also be talking about what are the components that a benchmark has and why each of these are relevant in their own way. Then I'll be discussing the actual setup for the monocular depth estimation challenge and how we try to take into account all of these different components. And then finally, of course, going through some of the results and the conclusions from the challenge. And just before we start, so a quick announcement again, in case you weren't here at the start of the workshop, and that is that the second edition for the Monocular Depth Estimation Challenge has been accepted and will be appearing at the next CBPR, so CBPR 2023, which is happening in Vancouver around mid-June. So we'll hopefully be releasing some new information sometime soon related to when the challenge will open, how to submit your predictions and deadlines and all that sort of stuff. So again, for this talk, one of the things that I want to discuss is some of these recent efforts that we've made into benchmarking monocular depth estimation, specifically components from this paper, Deconstructing Monocular Depth Reconstruction, which was published earlier this year at TMLR. And basically, one of the things we noticed is that in a lot of the existing benchmarks, we end up finding a lot of these common failure points. Some of the most extreme ones are things like having incorrect ground truths, uninformative metrics that don't really tell you extra information, and then slightly more subtle ones related to how we train our models, which include, for example, doing your hyperparameter tuning on the final test set. And then even more subtle is these not having really comparable methodologies and approaches. That means that they can kind of skew our results. So as I was saying, benchmarking really is one of the core components of every research field. And in terms of what a benchmark is or isn't, a benchmark is supposed to be a proxy for real world performance. That doesn't mean that it's actually going to reflect this real world performance. One of the main reasons for this is that, well, the real world is constantly changing and adapting. And if our benchmarks don't change alongside that, then they're not going to reflect this performance. A benchmark is also supposed to be introspective, where the metrics that we use tell us about how a model is failing and what are some of these failure cases. And it allows us to compare these different approaches to each other. A benchmark isn't necessarily supposed to be every single metric we can think of just slapped onto a table, because in a lot of cases, metrics might be redundant, some of them might be saturated, and if it doesn't provide any extra additional information to us, then there's no point in reporting it. And then finally, a benchmark is supposed to be a way of comparing these different methods to each other and trying to get an understanding for what contributions might be benefiting performance the most. It's not necessarily the holy grail for deciding whether a paper should be accepted or not, because there's a lot more to a paper than just how it performs on a given benchmark. There's obviously a lot of questions of novelty and how exciting some of these different contributions are. So in terms of components for a benchmark, the ground truth is really the starting point for any benchmark. You have a task that you're trying to perform, and you need to have the output for what that task should look like. And obviously, in this case, this means that if our ground truth is inaccurate, then potentially the whole benchmark is flawed because we're just measuring the wrong thing. Specifically, in the case of Kitty, we always use the vehicle LiDAR. And some of the problems with that is that the camera and the LiDAR are never going to be perfectly aligned, which means that they have slightly different occlusions. When you combine this with the fact that the vehicle is moving and that LiDAR is very sparse, it means that we typically end up with points that are apparently, sorry, I'm being told by Zoom that the slides aren't changing. Yeah, I'll stop. So currently, okay. Yeah, I tried to, I'll try resharing. Give me a sec. I couldn't see the Zoom chat, so I couldn't see. So I am, so hopefully you can see that. Let me just quickly check with Zoom. And hopefully I'm just gonna try changing a slide. So it should have gone back to the larger picture and back to the ground truth slide. No, they're saying still at the other slide. Yeah, I'll just try sharing the desktop. Yeah, weird. It seemed to work fine for the previous one, so let's just do the desktop then. Okay, so hopefully you can see again the slides. If we do this, okay, so I'm going to try, so we should be on the ground truth slide, and I've now tried changing to some of the picture slides. Okay, great. Being told that it's working fine now. Yeah, thanks. Don't know why that happened. Haven't really ever had issues with that. Okay, so I guess we can just restart from the ground truth. So again, as I was saying, the ground truth is really the starting point for any benchmark, because the idea is that we have a task that we're trying to perform, and we need to know what the output of that task should look like. And obviously, if this ground truth is inaccurate, then it means that our whole benchmark is potentially flawed because we're just measuring the wrong thing. In the case of Kitty, we're always trying to use the vehicle LiDAR as the source for our depth ground truth. And typically what this means is that our viewpoints for the camera and the LiDAR aren't perfectly aligned, because obviously they're two separate sensors, and that means that they have slightly different occlusions. When you then combine this with the fact that the vehicle is moving and a LiDAR is sparse, we end up with some points that end up being inaccurate, especially at object boundaries. And you can hopefully see that up here, where we have some of these points that are on the car surface, but actually we also have some points that are dark blue that are from the background that are bleeding in where the car should be. And you can see this, for example, again, in one of these other cars, and especially this tends to happen at these object boundaries. And with this, am I saying that this existing benchmark was useless? Well, no, not necessarily. It is worth noting that this inaccuracy only affects a relatively small percentage of points in the image. So again, these boundary points. And in the initial methods for monocular depth estimation using deep learning, so for example, Eigen and Fergus or Garg, this wasn't necessarily the biggest concern. We can see from the predictions that they're not really quite that detailed. And so in a way, having this slight inaccuracy doesn't necessarily affect the results of the evaluation that much. But at the same time, this does help to reflect the dynamic nature of benchmarks, where as research progresses, we care about different aspects of the system. And typically what we're hoping is that our research and our outputs get better and better. And so the level of scrutiny that we require from this quality of the ground truth also increases. So even though we're on Kitty, we can still do better. This is exactly what Uri et al. Set out to do to try and correct these limitations. And basically what they proposed was to accumulate the LiDAR over multiple frames. In this case, I think it was ±5 frames. And they also incorporated these consistency checks based on handcrafted stereo disparity estimates. And you can see that this results in depth maps that are a lot denser than the original ones provided by the Kitty ground truth. And also it just means it's more accurate. And again, we can kind of see this where now, if we're looking at the car, we don't have this bleeding effect where the background has been mixed in with the car. The one slight downside of this style of filtering is that because we're removing these inconsistent points, that actually tends to be the points that are at these object boundaries. And we know from our models and from visualizing these models that actually these depth boundaries are areas that are quite complicated for the models to predict. And so actually we would really like to be able to evaluate at these points, but of course only if they're actually correct. And so this is where we turn to the SINS data set that James was talking about earlier. And again, so as a recap, the idea is that SIN consists of these panoramas of LiDAR, of RGB images, and we also have the corresponding aligned LiDAR. And one thing that you'll notice is that actually the output of this LiDAR is dense, which in most of our outdoor data sets, because they rely on autonomous vehicles, a lot of times we end up with very sparse points from the LiDAR. Meanwhile, in some of these indoor data sets, we do tend to have this dense depth, but again, that tends to be indoors, which is not really a source that we end up using for training our models. And basically the way that SINS achieve this is that you have the LiDAR or the camera mounted on a tripod, and it's spinning with a very high angular resolution, which means that it's able to capture the scene very densely. At the same time, in a way, this means that each of these scans takes a few minutes to complete, and that makes them very sensitive to the presence of dynamic objects. So for example, vehicles and pedestrians, where you can kind of see that here in some of these images, where you can see these spikes, which actually, again, correspond to a vehicle being squashed by the capture. Since all of our deep learning methods don't really work with panorama images, we generate the SINS patches data set where we just extract crops from within these panoramas, again, of the aligned LiDAR and images. And essentially, we do this by sampling every 20 degrees, performing the whole horizontal rotation at eye level. And you can see that this results in these incredibly detailed maps where, for example, we have this very complex forest scene with a lot of trees, branches, leaves, but the LiDAR is able to represent this pretty beautifully. But again, as I was mentioning earlier, the main problem that we have is these dynamic objects. And to try and correct for that, we just do some manual filtering where we look through the images and make sure that we've removed all of these objects. And the artifacts that you've probably noticed is that, again, we have these like spikes, which represent cars that have been squashed. But actually a more subtle type of error that you might not have noticed is that none of the cars that were here in the image are actually here in the LiDAR. This car has somehow managed to vanish, leaving its shadow. And you can tell it's the same car because you can actually read the license plate on the LiDAR. This Fiat has somehow morphed into an SUV. And meanwhile, this Ford has somehow magically changed into a Jeep or a Jeep or a Land Rover, something like that. And again, the thing that's causing this is the fact that these scans take quite a few minutes to complete, and also they're captured sequentially. So we capture the image and then the LiDAR a few minutes after. And this means that dynamic objects that just so happen to be static during one collection might have moved by the time we actually perform the LiDAR collection. So this means that this manual filtering, we do need to be a bit more careful with it because it's not just detecting these like weird visual artifacts. We also need to actually pay attention to the content of the image. And again, so as I was saying, one of the main benefits of SINS is that we have this dense ground truth. And this means that we can use this ground truth to compute ground truth depth boundaries where we have these sharp changes in depth. And as I was saying, these tend to be the complex regions that our models tend to fail on. So again, evaluating on these areas might provide us quite valuable information about our approaches. The next component of a benchmark is the metrics. And the metrics are essentially the way that we compare our predictions to the ground truth. And I like to think of both of these things as a kind of meta-optimization, where if our ground truth and our metrics are incorrect, then our research will be trying to optimize the wrong things. And that means that we're kind of diverging from this case where we want our benchmarks to represent the real world. And so again, if these things are incorrect, then we're potentially guiding research in the wrong direction. And again, in the case of Kitty Eigen, which is the benchmark that everyone uses, quite a few of the metrics are either saturated, not very informative, or just incorrectly computed. You can see, for example, this is from a table from a recent paper. It doesn't really matter which. The main point is that, for example, for this delta 3 metric, I don't know, 7 out of the 10 existing methods have exactly the same performance, which is almost saturated at 100%. So in a way, this metric isn't really providing us any valuable information about like, okay, so which of these methods is performing better? And so this means that, yeah, we're reporting these things, but they're not actually providing us any useful information. And then also one of the interesting things is that basically since the inception of Kitty Eigen, this squared relative metric has been computed incorrectly. It's missing a squared term here in the denominator. And same as with the ground truth, people and authors have noticed this and know that this is incorrect, but everyone just still carries on reporting on this benchmark because everyone else in the past reported on this benchmark. And this is the only data set that people have results on. So if you're just copying and pasting results from previous papers, then you can't really do anything about it. So one of our solutions to this is that we're trying to incorporate some of these metrics from the official Kitty benchmark. And specifically, we're trying to favor those that are a bit more interpretable. So we have things like just plain mean absolute error, root mean squared error, relative error. And again, this tries to avoid some of these more saturated delta metrics, for example. One thing, however, is that all of the metrics that I've talked about so far focus on evaluating the depth at a single point. So we're comparing a single pixel in the ground truth with a single pixel from our prediction. But actually, in reality, the real objective of depth estimation is to try and recover the 3D structure of the scene. So maybe it makes more sense to try and evaluate depth prediction based on the reconstructed point cloud as a whole, rather than on the individual pixels. And this is precisely what Ornick et al. Proposed, where they use the F-score and the intersection of a union based on the precision and recall, assuming that if a point is within 10 centimeters of the ground truth, we assume that it's being correctly reconstructed. And one of the things they try to illustrate as, being the benefits of these metrics is the fact that if you take some very simple baseline, so the oracle is simply retrieving the image from the training set that has the closest, that has the best performance, or if you do something like just taking a median depth plane, then actually in a lot of cases, those simple solutions gives us better image-based metrics, so relative error, RMSE, than any of the developed deep learning approaches that we're trying to evaluate. But actually, if you then look at something like the F-score, which is trying to capture more if the scene has been reconstructed correctly, we start to see that these simple baselines don't work quite as well. And actually, we see some of this improvement from our methods. And then finally, since we have the ground truth depth boundaries from SINS patches, then we can also compute these metrics proposed by the IBIMS benchmark, where essentially we're looking at the chamfer distance between the predicted and the ground truth depth boundaries, which you can see represented here. Now we can finally get on to the actual monocular depth estimation challenge. And this basically represents kind of the combination of all of these aspects that I've been talking about. So the idea is that the challenge is based on the SINS patches data set, which is a lot more varied and has these much higher quality ground truth. We try to report these more informative metrics. Specifically, we rank our benchmark based on the F-score performance. And then as part of the challenge, we also provided the participants with with a dev kit containing some of these state-of-the-art implementations that have been updated to provide better performance. So again, just some visualizations from SINS patches, which kind of helps to reflect the diversity of the scenes here. So we have, for example, some more urban scenes, sometimes in more industrial settings, agriculture or farms, which, a very different type of man-made environment. But then we also have these very complex natural scenes with all of the branches and trees and grass and high frequency information. And then we also have some indoor scenes, especially focused on maybe things like cafeterias or lecture theaters. And as I was saying, we provided the participants of the challenge with a dev kit that contains 16 of these recent state-of-the-art implementations. And the idea was that we were trying to improve them all based on some common design decisions. And if you were at the keynote speaker from a couple of days ago, Kate Saenko, then this kind of sounds familiar, where basically what we find is that in a lot of cases, simply updating the choice of backbone to a more modern architecture from ResNext to ConvNext actually gives us more significant improvements in performance than incorporating some of these more complex state-of-the-art contributions. And one of the ideas with this benchmark was that we were trying to fix some of these discrepancies and inaccuracies that we tend to find in the training procedures, where, for example, people tend to train with different image sizes, different pre-training data sets, different sets of hyperparameters, or just different choices in architecture. And then, of course, one of the most subtle ones is this idea of cherry picking, where if you train the same model 4 or 5 times, you're always going to get slightly different performance. So it's very easy to just take the best performing model out of those and report those results. Whereas we find that it's a lot more stable if you just train these multiple models, but report the average performance instead. It gives you a more stable result. And so based on this benchmark, based on this dev kit, we provide the baseline for the challenge, which Oshin was talking about earlier this morning, which is essentially this GARG baseline, which was literally the first approach to self-supervised monocular depth estimation, which just relies on the stereo support frames and the plane photometric loss. And then finally, we can get onto the actual results. So in the end, in the challenge, we had 4 valid submissions from 4 different teams. Team OPDAI included a lot of these contributions. So I'm going to try playing a video that they sent, because unfortunately they weren't able to attend the workshop in person, but hopefully this video works for both online and here.
Hello, everyone.
Hopefully you can hear it online.
And here we would like to congratulate on the success of this workshop. Next, I'll briefly describe our solution in this competition. First, for the data representation, we use the SBEM method to generate copy attachment. We're certifying our submission and the final score that 6% was able to improve by almost 1.0. Second, for the best prediction network structure, we chose our next speed as the encoder. While for the choice of encoder, we chose Jaime and Hertz, which improved F-score by almost 0.1 compared with more depth model. Third, for the loss function, we use a series of combined losses, including the photometric loss with an explainability mask, autoencoder feature-based reconstruction loss, virtual stereo loss, proxy depth regression, age-aware disparities nucleus, feature nucleus, occlusion regularization, and explainability mask regularization. Lastly, for the specific training setting, we set the mean rate to 0.0001. The optimization method to Hayden. The bench size to 4, the chain echo 5 with using a V100 graphics card. While we achieved improvements in several traditional metrics in this competition, we failed to improve the point cloud soil construction. This shows that the science tech dataset is indeed a trending dataset. Unfortunately, we only use the 50 dataset for training in this competition. Perhaps our results could be further enhanced by introducing the 60-stage dataset into our training. Okay, that's all we have to share. Thank you for listening, and let's switch it for the next presentation.
So yeah, thanks again to the participants for providing that video. The next theme was Z-Zuri. And again, we see this where, again, simply just using this convex backbone typically is what gives us that improved performance. And one of the main contributions of their method is that they incorporate this pose regression where, in addition to giving it the monocular sequence, they also give it the stereo pair, which has a known baseline, and try and regress the pose based on that. And this team will be giving their presentation straight after this one. It was supposed to be at 11, but we're running slightly late. But yeah, they'll be on immediately after this one. The third team, unfortunately, didn't provide any additional details. And then finally, the fourth team we have is MonoVIT, which actually, instead of using this Convex backbone, uses their own MonoVIT architecture, which is a combination of convolutional blocks and MPVIT blocks. And the main contribution from their approach is to use proxy depth regression, but instead of using handcrafted disparity, they actually train a separate self-supervised stereo depth network and use that to distill the depths onto the monocular one. And they'll be presenting after the next team, which will probably be at around 11:30. Here you can see some of the results from the actual performance on the benchmark. And this kind of team OPDI was mentioning, one thing that we find is that all of these submissions typically improve quite a bit on the image-based metrics. So we can see that in this case, for example, the mean absolute error is improved by 30 or 40 centimeters. RMSE is somewhat close to a meter, APSRO by a few percentage points. But actually what we find is that when we evaluate these in terms of the F-score, we don't see much of an improvement or change in performance. And part of what we think is the reason for this is, again, that throughout, since the inception of these tasks, we've always been evaluating them based on these pixel-wise image metrics, whereas this idea of evaluating it based on the point cloud reconstruction is relatively new. And this means that all of the contributions that we've developed over time have tended to focus on actually improving these pixel-wise metrics, but not necessarily on improving the reconstruction. So I do think that, for example, trying to improve this metric is really the way forward, because it feels like it gives us more information about the system. Some analysis that don't really have time or space to show here is that we actually provided an additional breakdown of the results based on the type of scene from SINS patches. So we provided these same metrics, but for example, only for outdoor forest scenes, outdoor urban scenes, or indoor scenes. And typically what we found, as kind of we expect, is that all of these models tend to adapt better to other urban scenes, because again, all of them tend to just be trained on Kitty. So again, even though this is a slightly different type of urban scene from Kitty, like the models still do relatively well. But then as soon as we take them to something like forest scenes or indoor scenes, they struggle a lot more to adapt. And to highlight some of these cases, some of the main things that we see throughout these predictions as main sources of errors, for example, along these thin structures, a lot of times the model will just kind of interpolate across them and just fill in the gap and treat it as a solid object. In the case of indoor scenes, sometimes we see these just errors in like relative depths where, for example, this marker is predicted as being quite a bit closer than it should be, or we just lack a lot of the detail in the books. And then, of course, with natural scenes like these forests, as kind of Ocean was also talking about in his presentation, was models like this struggle on thin structures. And obviously a forest is basically almost entirely composed of branches, tree trunks, but also this high frequency information from either the tree leaves or just the grass on the floor. And so basically that's it for the presentation. Throughout this talk, I've talked about the importance of the benchmarking procedure. Obviously, this talk has primarily focused on depth estimation, which I'm guessing if you're here, you're somewhat interested in. But if you work on different fields, then it's definitely something that I would recommend taking a step back and re-examining. Think about what benchmarks are being used, what metrics are being used. Are these ways of comparing methods actually fair or not? Because this is a very important topic that, actually helps us advance our research. And so, yeah, just for some other conclusions. So what we found is that actually these classical methods, so even literally the first self-supervised stereo approach, is still very highly competitive when you compare it to recent state of the art. And related to that, point cloud F-score metric is a very important and challenging metric to actually improve upon. And also from these results, it also seems quite obvious that just using driving data isn't really enough to train these generic models. And if we want to train these models, then we need to find additional sources of more varied data. And also as a reminder, we will have the second edition of the Monocular Depth Estimation Challenge happening later this year, and we'll be updating these announcements probably via Twitter, via these two accounts. So if you're interested in keeping along, then follow along, and yeah, we'll just release the information as it comes out. And yeah, finally, we probably have, again, time for maybe 2 or 3 questions, but yeah, Other than that, afterwards, we'll see presentations by the challenge participants. So yeah, thanks.
Thank you for putting together this elaborate data set. I really like the using the App Store to capture more of the myself have worked with this quite a bit, and that Delta one or Delta two was there that really, people were doing like 25% error and doing counter systems. Like an object is 1 meter away, you estimate it as 1.25, so it has. It's quite typical, right? That's not good for the manipulation. So the other thing I want to ask is just the efforts to really capture even the it's still a number, right? So you still have to scale to some extent. Most of the methods don't do that, right? So I was wondering if there are metrics, I don't know if you showed it in that list of metrics, but something that captures how well you're estimating the relative scale. Because what I have seen in methods is maybe when you're nearby or nearby objects, the scale is reasonable or it's linear, and between what you estimate and what the truth is. But as objects go farther away, what happens is that scale starts to vary a lot, it becomes non-linear in that section. And for analysis, for path planning purposes, okay, nearby is one thing, but far away is you have large variation in the scale. So that'll be one metric to capture and say, okay, method is predicting this. All the MSC and everything is still pixel by pixel. I want to say that on the whole, right? You still average it over the entire image, and a lot of detail is lost. Being able to look at it, saying maybe as a bin-wise, saying like, for the first 5 meters, this is the average error. 5 to 10 meters, this is the average error. Gives a much better idea of further use. Everybody wants to do something in the depth, and that's why we're doing it in the first case. And one thing is that was in this slide. So you want to say that. Yeah, so anyway, those just some of my. I'm looking to see if they have metrics that look at it as a distribution.
Yeah. Okay, cool. So yeah, I'll repeat that for the online audience. So the question was also some comments on the fact that, yeah, evaluating with this F-score seems quite a reasonable thing. And in a lot of cases, people report these delta metrics where you might have an error or a depth prediction of 1 meter and your prediction is 1.25 meters. And that's really not acceptable in terms of accuracy levels. And then the actual question was, if we have any metrics that reflect the relative depth. So for example, what we might tend to see is that at closer range depths, we end up having smaller errors, whereas the farther away you get, the more these errors tend to increase. And again, this change in performance might be even linear or just exponential based on this increasing depth range. And so basically the answer is that, I guess in sense of the metrics that we're reporting, Abstrel is the closest that we have to that, because the idea is that it's reporting the relative error. So again, so that means that if we have a 30% relative error, then if you have an error of 1 meter, prediction of 1 meter, then on average it's 30 centimeters. Where if it's 100 meters, then on average it's wrong by 30 meters. So in a way, that's the only metric that we currently have capturing that. But something that I've seen in other papers is that they do essentially have these evaluations where basically they perform this evaluation at increasing thresholds of depth. So they say, okay, if you only consider points that are from 0 to 20 meters, then our metrics are, we have an error of 1 meter. If you increase it to 40, 60, 100, then we typically see that, yes, that these errors do tend to increase with the average depth. So again, in this case, we don't report that, but it could be an interesting thing to do, because obviously our intuition is exactly that for things that are closer away, they tend to be a lot easier, whereas especially in the far range, it can probably be quite wild. Was your question also related to the idea of using relative depth rather than metric depth, or was it more about like the depth range?
Metric depth, really, usually And if you guys look at the distribution of the depth in your data. So
Right.
Previously plotted the IPT sets and distribution, and you can see there's a nice that there are 5 or 6 meters, and then it's like around.
Right. So
Even in the sequence 1, which has a longer tail, it's like in the highway sequence, or can I forget?
Right.
Has a longer tail. So that sequence, every paper you will find will have larger error just because it was not in your training distribution. So one other thing was possible to ask was, look at the distribution of the depth in your data for different scenes.
yeah. Okay. So the follow-up question to that was related to the distribution of depths within a scene, where, for example, even just different driving scenes might have different range of depths. And I guess the more extreme case, if you suddenly take that indoors, or if you take it to a field where there aren't many buildings and stuff, then you'll probably have much larger ranges of depths. And yeah, we did a quick analysis of the overall data set, where we basically do see that, for example, on Kitty, most of it is centered, I think, yeah, around like 10 meters or something like that. But the maximum depth goes up to 100 up to 80 meters. Whereas on Sims patches, we also have an additional bump at kind of lower depths, because that kind of represents those indoor scenes. Then we have the outdoor scenes. And then in this case, the maximum depth actually ranges to, I think, 120 meters or so. Per scene, we haven't really done an analysis, but yeah, that's definitely something that, again, if you're talking about all of this domain adaptation and transferring from Kitty to other scenes, then that's definitely something quite important to take into account. So yeah, that could also be interesting further analysis. Yeah, I think we'll do one more quick question.
Okay, just a idea for the CPR workshop. So we know the new perception and surface orientation perception. Some of the earlier models algorithms and explicitly was a loss on surface orientation estimates, right? So, or yeah, really. So in the published Sims data set, we didn't publish surface orientation, but in the paper, we developed a method for estimating local surface orientation, and that's what these statistics reporting is for. So it's pretty, I think it's pretty good round trip estimate of surface orientation. So one of the years to method for evaluation, which is not a program surface orientation. And I think that would be useful for many implications. And also, I think related just in human perception. So, for example, complex scene humans are found pretty good at judging surface orientation. 2 points are quite distant from each other. Integrating that to figure out which one's closer. So, anyway, just another possible.
Right. Yeah. So this question was that, again, in the Sims data set, we have the ground truth, but there isn't really ground truth information for the surface orientation. But there are ways of estimating this quite reliably, and that actually this might also serve as a good metric to report in the benchmark, because the quality of how we predict these surfaces then also kind of tell us, or we know that humans are sensitive to these kind of changes. So actually this metric might also tell us more about how these models are performing in a slightly different way. And yeah, definitely that sounds pretty interesting. I know that there's been a few methods recently that actually use surface orientation during training instead, where I think they predict the depth map and they try and refine it such that the surface normals are also consistent with each other, or like a smoother, which again tries to remove some of these like weird textures that we sometimes see in the predictions. So yeah, that's definitely something that could be quite interesting to report. So yeah, thanks for the suggestion. Cool, great. Well, thanks for that then.